Hello. All right. We're going to start this lecture. I'm going to give you a summary or kind of summary of what we have discussed so far. First, I'd like to say a few words about time frequency analysis. What we are doing in this semester is really about time frequency analysis. However, in the field, this term, time frequency analysis, has been used primarily by the double E people. And they, unfortunately, put the time frequency analysis as the sole representation of Wigner-Wild distribution. We'll discuss that. So yeah, the frequency and
sorry, excuse me. We cannot see the slide on the screen, but could you send us a slide? PC screen.
Oh, you cannot see the screen. Okay.
Screen.
Sorry, our technician is trying to fix it. Hold on. Let's
Okay.
wait for a couple of minutes. Okay.
Okay, sorry. Thank you very much.
Thank you for letting me know. Okay. Can you see it now? Hello?
Yes, we can see it now. Thank you very much.
Okay. All right. Now let's start again. As I said, the time frequency analysis, the term time frequency analysis, has been hijacked by the double E people. Most of those people actually are doing Wigner-Wild distribution. Now, why we're doing time frequency analysis? Because most of the phenomena that we see, both frequency and energy level are actually changing constantly. For example, when we talk, we listen to music, and even when we experience the weather, the temperature fluctuation, it's changing. They're all highly variable. So traditional frequency analysis is not adequate, because traditional frequency analysis is average frequency, not really give you frequency at that particular time. So we developed this new method of time frequency analysis. It's trying to describe a phenomenon, not only on its frequency domain information and energy domain information, time domain information. We want to describe the variation of both time and frequency change as function of time. Yeah. So what is time frequency analysis? The time frequency analysis, there are many of them. Probability is not time frequency analysis. Spectrogram is. Okay. Wavelet is. Wigner-Wild distribution trying to be, yes. So those three methods are the time frequency analysis method that we know. All right. So all time frequency analysis should be regarded as time frequency analysis. For example, like wavelet. However, if you go to the double E community, a communication engineer, they will never regard wavelet as a time frequency analysis. They only regard Wiggen-Weil. So as a result, this term, time frequency analysis, is monopolized by Wiggen-Weil. And I don't think that's right. So condition for time, what is a time frequency analysis? We have to have a valid method to express frequency as well as time vary with frequency and energy vary with time. So anything to describe that, it means the frequency and the energy has to have instantaneous value. If you don't have instantaneous value, then you will never be expressed as a function of time and keep fluctuating. Yeah. So not only that, ideally, we should be able to separate the events. If two events occur, they are uncorrelated, unrelated, we should be able to tell A and B separately, not together. Yeah, I will show you why we say that. Let's see, wavelet. Wavelet. This is the simple definition of wavelet. Any wavelet is defined like that way. We have a normalized normalized factor, and then the key part of the wavelet is this: is A and B. This B is called the translation. By changing B, you actually move this function, the center of 0 point of this function, along the axis of time by changing B. But by changing A, you actually make that window wider and narrower. Yeah, a very large A means a large wide window divided by A, it becomes small. So large A means you concentrate the window in one local area. Okay, and small a means a very tiny area get expanded wide. So these are A is dilation factor, B is translation. So by translating and dilating the window, it becomes very versatile that you can look at one local area in details, and we can look at the area in a very large window too. Yeah, depends upon frequency. So this dilation is actually related to frequency. Yeah, it's not totally independent. Now, what is Wiggen-Weil distribution? Wiggen-Weil distribution is our frequency is defined this way: the time t and time t plus tau. Correlation function make a Fourier transformation. We call that spectrum. Wiggen-Weil it's different. Wiggen-Weil says that instead of the t, we make it t minus tau and t plus tau. It's still centered around t, minus a half plus 1/2 tau. And then this transformation gives you W. This form and this form are very, very close. The difference is that once you get this W, you still retain this variable t. Here, you get this. You forget about the t because this t is independent of t. We only deal with tau. So Wiggen-Weil is to consider the possibility of variation of the correlation function. Yeah. Now, once we do that, then how we define instantaneous frequency? Because this is a Fourier analysis, it's independent of time. All right. So at each time, you only get one spectrum. What you're getting here is that at each time you get one spectrum. You move another place, you get another spectrum. If, for example, we have a signal arbitrarily changing. Now, what you do is that you compute autocorrelation function here and autocorrelation function here will be slightly different. So each time you do a Fourier transformation, you get a spectrum. If you center around here, you get this. You center around here, you might get that. So then what is Wigner-Weil? Wigner-Weil is that you get this spectrum everywhere. Then you contour this spectrum. This distribution is called Wigner-Weil. So it indeed consider a little bit of the time variation. The final result has some time information. But then at each point, you only get one spectrum. How you define instantaneous frequency? The instantaneous frequency is defined by this moment method. You take the W, take the first moment, and compute the value of it, and rectify it, and normalize it. So Wigner-Weil, I don't like this at all. This Wigner-Weil, in this way, this frequency, even though it's a function of time as it's changed, but this is a mean frequency. If you go to a concert, and then it will give you one frequency. That frequency is neither the drum nor the violin, but it's the average of the two. Yeah. So not only that, this has another very, very serious flaw, is that if we have two independent events, this method will not be able to separate the two independent events. Let's see what it means. Then finally, we have a short-time Fourier analysis. Short-time Fourier analysis is a Fourier analysis plus a window. Window is at a given time and delta t, how wide the window is. Once the delta t is chosen, then the width of the window is fixed. So the disadvantage of using this window is that once you choose the window size is constant. For high frequency, you have better resolution because for a given window in high frequency, you get many, many waves. For low frequency, you probably will not even cover one wave. So the resolution is very ununiform, very non-uniform. For high frequency, you have redundancy of resolution. In low frequency, you don't have enough. Yeah. So that's why the wavelet, when wavelet first was introduced, wavelet said, look, our wavelet resolution is uniform resolution because each wavelet has the same number of waves. So the resolution power is uniform. Yeah. But unfortunately, in order to have the wavelet, to have frequency resolution, you should put enough wave in the one wavelet. But if you put too many waves, then it will not be local. So in between this local and resolution, you hit a compromise. For example, like the commonly used monad wavelet is the most common and one of the early wavelet used. There are only 5 waves in the window. In other words, your resolution power is limited by 5 waves. Okay, so the resolution, even though it's uniform, but it's uniformly poor. Yeah, nowhere the resolution is good. Everywhere it's relatively poor. Okay, now what is the so-called additive events? If we have a function x plus a function y, if we do Fourier analysis, the Fourier analysis of x equals s1, which is Fourier of 1, x2 is Fourier of 2. So Fourier transformation is a linear transformation, so it is additive. 2 events is f. But however, if we know that when we do spectral analysis, the spectral analysis is not Fourier transformation of the signal. is the Fourier transformation of the correlation function. The reason that we use correlation function is Wiener-Crunchin theory. Yeah, we need that in order to prove it converges. So if we use S as square, because it's squared, so S1 plus S2 squared is S1 plus S2 plus 2 times S1 times S2. So this does not equal to S1, S2. So when you have two events, the wave spectrum does not linearly add up. Yeah. All right. So because of this, the Wigner-Weil people come up with a why they can monopolize the term time frequency analysis, because they cooked up this requirement. This requirement is called the marginal requirement. What's marginal requirements? Marginal requirements is that if I take a data, if I do a Fourier spectrum, I put it on side. Then you can do whatever. When you do other spectrum and you add up all the time frequency, you have to come back to the Fourier spectrum. If you cannot come back to the Fourier spectrum, it doesn't count. It is called flunk, the marginal requirement. So because of that, only Wigner-Weil method satisfies this marginal requirement. Because Wigner-Weil is Fourier, so its marginal value is Fourier. Let's see, is this reasonable? It turns out this is a very unreasonable requirement. Because if the Fourier spectrum analysis is based on linear and stationary assumption, so whenever you apply to a frequency variation, time variation, and energy variation, it already violated the assumption. So you create a marginal spectrum, that marginal spectrum is already unreasonable. So if my marginal spectrum equals to your unreasonable result, it's equally unreasonable. So this requirement is put up by the Wigner-Weil, but I don't think it is a reasonable and logic requirement. So let's see. Suppose we have two waves, wave 1 and wave 2. They're propagating. Yeah, they're propagating. They can move. See, from this position, this wave is moving that direction. This moves to the other direction, and so this wave is moving toward this wave, and then you can see that the wave, the relative position of the wave is changing, and at all the time, these two are independent. They're not interacting. Only at this time, they start to interact. Yeah. So if we have this situation, we have two gentlemen. One gentleman generates wave here, the other one generates wave there, and they start to propagate. If we give this to Wigner-Weil, can they separate these two events? No, because the Fourier analysis is global. Each of their spectra is global. So at this moment, if I choose zeros here, I have 2 here. By this time, it changed. The autocorrelation totally changed. This is very different from wavelet and spectrogram. Spectrogram says, I only look at this window. I don't look at anything else. In this window, I see wave. I didn't see that. So I can separate these two events. Wavelet can do it. Spectrogram can do it. But Wigner-Weil cannot. Because Wigner-Weil, at every moment, is take the whole information. As a result, if, for example, if I choose this to be my time 0, even though I have no events, but you will have a lot of energy, because the correlation function over there will give you a lot of energy. But if I put a wavelet here, or put a spectrogram here, I have nothing. Yeah. So this cross events, crosstalk, make Wiggen-Weil very strange. Not only that, in the in this slides, we have the product, and these products can be both positive and negative, and sometimes it can be, you can cook up a situation that this term is very large and they can cancel the two almost to zero. Yeah. So in that case, how can we get rid of this cross term? So that is another issue. So some of the people come up with a filter. It's called the kernel, and it's to suppress the crosstalk. Now, if we take this and if we compute the Fourier spectrum, you see, it depends upon where the wave locates. You get very different Fourier spectrum. Yeah, because you get a very different spectrum, and then when you do Wiggen-Weil, you will have all different kinds of energy distribution. How's the energy distributed? It looks, if we take the previous case with one wave, low frequency here, high frequency wave here, using Hilbert spectral analysis, we have a very clear frequency here and very clear frequency here. They are totally separate. Okay, as this thing coming close and eventually get past each other, this and that stand clear from each other. Now, if I do it wavelet, it's also clear. Now the wavelet, because of the frequency resolution is poor, they give you this much of a spread. This is the integral. Wavelet give you this frequency distribution, and higher frequency give you that distribution. Even though the frequency is not as clear as clearly defined or precisely defined, but the two events are separate, and you can propagate this across each other. You can still track the two wave package clearly. But what if you do Wiggen-Weil? Wiggen-Weil, for one event, you get this. At zero, frequency is not zero. The second event, you get that. So if you put this event and that event, if these two are additive, then you should be able to still get one event and another. But if you put it together, you get this. You get both this event and that event and the crosstalk. In other words, at a point where we should not have energy, the energy appeared. Yeah. This is what we called the crosstalk. So the Wiggen-Weil people know this. They devise all kinds of methods to eliminate that. So finally, they get one filter which can eliminate, in lots of cases, eliminate that, and they call those functions Cohen class function. Those functions that can eliminate that. But that's not really physical. So if we put this together, we see energy here, but all these are cross terms. And this compare to the two components, and you will see that this is Wiggen-Weil, this is wavelet, and this is Hilbert. The difference is that much. And this is Wiggen-Weil, this is wavelet, and this is Hilbert. So Hilbert gives you a very precise definition of frequency. Each of these waves that I put it in is a Gaussian modulated sine wave. So the frequency should be constant, yeah, even though the amplitude is not. Now what are all this? This is very, very difficult to. Later we'll see more. So you look at this wavelets, you look at the marginal spectrum, you'll find that at the different marginal Hilbert spectrum, they give you the wave very clear, sharply defined at each location. Yeah, they're slightly crosstalk, but here is this part is the wavelet. The wavelet is so widely, smoothly spread, but for weak and wild, you will never be able to do this. Let's now take a example of the length of day. The length of day data, if we do a spectrogram, you see how many harmonics we got? This actually is the half monthly time. Yeah, this is cycle per year. Half monthly is about 26 cycle. It's here. Now, all of this are harmonics of this. Yeah. Not only that, the resolution is determined by the sampling rate. So one data a day means each year gets 360 data points. So as far as cycle per year is concerned, your Nyquist is 180. You cannot change that. All of this are wasted. You don't have any information here. Yeah. Now, let's look at the spectrogram if you want to look at the detail. Because you waste all the resolution, you come down here, you start to see the cross-grain structure. This is still the half monthly, and these are the harmonics, and these are the annual cycle is around here. Yeah. So it's very crude. Now, if we do it weak and wild, this is weak and wild. Yeah. Even after you suppress that, so what do you do? What do you have? So this is half monthly. Yeah, this is monthly. Yeah, all of this pattern, the crosstalk. It is very, very unclean. Yeah. And then, if we do it the Hilbert way, the Hilbert gives you half monthly, and around monthly, and annual, and half manual, half yearly. So this gives you a very clear definition of annual cycle, half annual cycle. By comparison, you see here, the annual cycle almost get washed away. You don't get anything. And here, you get a very clear definition of that. Not only that, the half monthly here, it's spreading. Why it's spreading? Because it's nonlinear. Yeah. This is not because the frequency definition is no good. The instantaneous frequency is very precisely defined how the waveform changed at that point. If you look at this, you can see this is monthly, it's half monthly, half yearly, yearly. It's very clear. This is not as clean as the definition on that screen. So now we can see that the wavelet, if you look at the previous is wavelet, this is Hilbert. Yeah, even wavelet already give you that, and Hilbert give you this, and all of this fluctuation is an indication of nonlinearity. So the summary is a wavelet spectrogram and HHT can all separate simultaneous events with different degree of fidelity. Yeah. Some can separate better, some can separate it slightly worse. But weak and wild cannot. If you have two events, the two events start to crosstalk. Yeah. And because of that, they say, all right, we define frequency by moments. So their instantaneous frequency then becomes a moments computation. So it's a weighted mean of instantaneous frequency. Yeah. Even though wavelets satisfy the so-called marginal energy requirement, it does not mean that it's better. The marginal energy marginal energy requirement itself is illogical. Yeah. Therefore, even if you satisfy that, there's no claim for superiority just because you satisfy this. For somehow, after they define this, they feel pretty good because they say, eventually I'll come back to Fourier spectrum. That's great. Their misunderstanding on frequency is profound. I will give you, I will discuss why I think their misunderstanding of frequency is profound. It's very deep. Yeah. So now we know when you go out, people ask you what's time frequency analysis. You can very articulately tell them that what is time frequency. Time frequency means both frequency and energy has to have instantaneous value. And this instantaneous value should be independent of other interference. Because of that, we can see that the wavelet, spectrogram, and HHT are all time frequency analysis methods. But even though the time frequency analysis method, the term has been monopolized by Wigner-Weil, but I don't think Wigner-Weil is a time frequency analysis method because it flunked the instantaneous value, not because it satisfied the marginal. Marginal doesn't count. Okay? All right. So this is the summary of time frequency analysis. Now, the next I will again talk about the instantaneous frequency. If you learn anything at all in this semester, you learn how to define frequency. This definition of frequency is the key to everything you want to do. The key to do time frequency analysis, the key to define nonlinearity, the key to define non-stationarity, the key to define trend and detrend. Everything starts from this idea of what is frequency. And the only true definition of frequency is not from Fourier, not from 1/period. The true definition of frequency is time derivative of phase. This is the whole thing in this, the core, the central idea, that everything that we talk about is because of the definition of frequency was not good. In the past, they have never done a good job on frequency definition. Yeah, Fourier is no good, wavelet is no good, nothing is good enough for us. Now, once we define this instantaneous frequency, there are some people start to find arguments against our definition. Yeah, the chief challenger of instantaneous frequency is this gentleman, Leon Cohen. Leon Cohen is a professor of physics at the Hunter College, the New York City College. New York City College is a very interesting college. It's set up to serve the citizen in New York. New York City is a huge, big place. The population, including the suburbs, is probably more than the total population of Taiwan. Yeah, so it has city colleges, many campuses. Yeah, it's very cheap. Yeah, and because New York City has a lot of people. Yeah, So there are lots of smart people. So New York City College is so inexpensive, many people can attend. So many people call the City College the poor man's Harvard. Yeah. It's a very good school. He's a professor there. Yeah. I met him once. He is a typical New Yorker. You know, if you live in a big city for a long time, many people live together. You have to fend for yourself to define your space for your life. So you don't want people to get too close to you. He's exactly that kind of people. Yeah. He wrote a book. The book is Time Frequency Analysis. Yeah, Prentice Hall, 1995. This book has been cited a lot, more than 1,000 times. Maybe now reached 1,000. I didn't check. Yeah, mostly by double E people, because double E people really like this word, time frequency analysis. Yeah, maybe they are now getting lesser and lesser so because the signal analysis community start to see this is no good. Okay, for example, Delano Mendiach is one of the editors. He started to publish papers on EMD now. Yeah, so I think EMD eventually will supersede this. But for a long time, time frequency analysis is working well. And who is pushing that? Leon Cohen. Yeah. Once I had a meeting as two giants clashed. Leon Cohen was there. He represented Wicked Wow. The other gentleman is David Donahoe from Stanford University. David Donahoe is one of the Wavelet person. Okay. David Donahoe and Ingrid Derbyshire were elected to National Academy of Science in 2002, I think, well, somewhere around there. Both of them get elected to National Academy of Science because of their contribution in wavelet analysis. Yeah. Now, if you read the wavelet, this is another interesting thing. If you pick any book, read the wavelet analysis, they will never mention time frequency analysis. Never. Okay. If you ask Ingrid Derbyshire, is wavelet time frequency analysis? No. Wavelet is for data compression. Yeah. Why? Because it's integral method. The frequency is ill-defined. You do have this conflict. Yeah. So when Leon Cohen met David Donahoe from Stanford, it's two contrasts of style. Leon Cohen is very cocky, very aggressive, and start to say many bad words about wavelet. And David Donahoe is a super polished guy. David Donahoe is educated in, I believe, in Princeton and Harvard. So it's super smooth. And each word he used are very measured. Never use any crude word. Yeah. So the two were arguing. Yeah. Like one very rough guy meet a very gentlemanly talk. Their interchange is extremely interesting. But I would say that Leon Cohen is a representation of this. In his book, if you read his book, there's one chapter called Instantaneous Frequency. After he discussed instantaneous frequency, he posted in chapter 2, Instantaneous Frequency, page 40. If you see this book, you will see. He posted these 5 questions. Yeah. Because this is the last time I would teach this course, the last class this semester. I'd like to have a little bit of interaction among people. This 5 objection, what he called a paradox. Yeah, he called a paradox. He said that even though we can define instantaneous frequency by Hilbert transformation, but here are the questions to prove that the instantaneous frequency is not reasonable. Yeah. How unreasonable it could be? Let's look at this. Let's look at this the question that he raised. Question number 1 is instantaneous frequency of the signal may not be one of the frequency in the spectrum. Listen, here first we have to define what is spectrum. Spectrum is a Fourier spectrum. Okay, spectrum is Fourier spectrum here. Yeah, he said that the instantaneous frequency signal may not be one of the frequency. In other words, you take a signal, you do a Fourier spectrum. Then you calculate the signal, the instantaneous frequency. You find the instantaneous frequency different from the Fourier spectrum. Not only that, the Fourier spectrum may be a spectrum, but the instantaneous frequency can be outside. So that is a no-no to him. So spectrum should be the standard. And if you violate that standard, it's no good. Okay. Second, a signal with a line spectrum consists of only a few sharp frequencies. So suppose you have a nonlinear wave. You do that, you get a fundamental harmonic, very sharp line. Or I get one frequency, another frequency, third frequency. It's all very clear. But then the instantaneous frequency may be continuous. Yeah. Specifically, if I have fundamental harmonics, and when I do a full instantaneous spectrum, it's continuous over a range instead of covering this. So this is another cardinal thing. It's, again, an unforgivable thing. This is a paradox. It's no good. 3, although the spectrum of analytical signal, is 0 for negative frequency, the instantaneous can be negative. This is, again, he cannot. He said, how you do instantaneous frequency? Based on Leon Cohen, there's only one way to do Hilbert transformation. How's Hilbert transformation implemented? Hilbert transformation implemented by Gabor's, later we'll talk about, by Gabor's algorithm, is that you take a signal, I will give you this again. You take a signal, you do a Fourier transformation. You get both positive and negative frequency. And then you say, all right, I will set all this equal to 0. Yeah? And then I only maintain the real part, and I Fourier transformation of that. Yeah. And that's my, that actually indeed is a Hilbert transformation. Fourier transformation, inverse Fourier transformation. Gabor's implementation. And we can prove that it's Hilbert transformation. He said that you have already taken the negative frequency to be 0. And now from this, you can calculate the frequency, still get negative frequency. That is, again, wrong. Yeah. Now, the fourth is the band-limited signal. If my signal has given a frequency band, yeah, and then the instantaneous frequency can be outside the band. You already told me that it's band-limited. How can instantaneous frequency be beyond that? Yeah. The fifth, I think maybe the only valid point, is the value of instantaneous frequency should depend only on the present time. Yeah, it should not say from negative infinity to positive infinity. But when you do Hilbert transformation, the integral is from negative infinity to positive infinity. So your instantaneous frequency is not built by the information at this moment. It's built by the information of all time domain. So how can that be an instantaneous frequency? So all of this objection that he raised. From that, he says, look, instantaneous frequency is no good. We have to do within a while. And then how to define frequency? We do a moment. And during the moment, you will never go beyond the spectrum. You'll never be negative. You have everything. It's great. And satisfy the marginal requirements. This kind of argument comes the so-called the leading authority in time frequency analysis. It's shocking. It's shocking to me. When I read this, I cannot resist my chuckle. I will keep laughing at this kind of frequency. What do you think? You ask yourself, can you explain any of this? Explain to him that this is wrong. 你们能不能 Can you think of the reasons to tell them it's wrong? All right. By spectrum here, Lee and Cohen is limited to Fourier spectrum. By instantaneous frequency, he is getting the frequency by Hilbert transformation. Yeah. If you don't do both of this, then a lot of his question is not important. Yeah. For example, I can tell you a little bit. We do instantaneous frequency not by Hilbert transformation. If we don't do it Hilbert transformation, it's not over the whole time. So the fifth objection is not important. It's not right even. Yeah. Instantaneous frequency could be defined by the present information. By what? By quadratures, right? We don't have to do. We don't have to take integral. So the fifth objection is fixed paradox is not important at all. Yeah. Now, with this in mind, we'll look back his 5 paradox. The paradox 1, 2, and 4 are essentially the same. Instantaneous frequency may be different from the frequency of the spectrum, either bandwidth or sharp lines or whatever value. Your instantaneous frequency is not one of those. Second, negative frequency of analytic signal seems to violate the Gabor construction. That, again, that is one of the objections we have to answer. This actually is one class. This is another class. Finally is a Hilbert transformation. Hilbert transformation can diffuse that without any problem because you say, yeah, it is an objection, and we agree. Yeah, but we can get around that without any difficulty. Yeah. So let's see the first one. To resolve paradox 1, 2, 3, 1, 2, 4. If we have sine A plus B, yeah, then the Fourier give us 2 frequencies, one of this, one of that. Yeah, 2 line. But the instantaneous frequency, however, it's constant, with a singular point here. Where's the singular point? Singular point is occurred at amplitude equal to 0. Sine A plus sine B has one point, the amplitude is 0. The amplitude is 0, we cannot define frequency. So the frequency is constant, This is Hilbert spectrum. Now, if I use Fourier wave, but I use, instead of Hilbert's, use Fourier spectrogram, this is the spectrogram. What you see is that, again, the frequency is around here, energy fluctuate, you have negative frequency. Yeah. Negative frequency, it's hard to say where frequency is. Here I can say the frequency is here. Here it's all connected. Frequency is ill-defined. Okay? Now we use wavelet. Wavelet is this. Yeah. And for Hilbert spectrum, we have frequency constant. Here we get the frequency blew up in a big ball. Yeah. And instantaneous frequency give you the frequency actually has very sharp value. Now, if you use normalized, you get this a little bit better, but still you have a singularity at 0 point. And if you blow up, you can see the singularity. We do have a singularity when it's 0. Now, what happened here is that Fourier gives you 2 peaks. We give you only 1 peak. Is this wrong? This is different from the 2. Is it wrong? It's not wrong, because sine A plus sine B has 2 representations. One is sine A and sine B. The other one is cosine A plus B and sine A minus B. Yeah, this is it's modulated. So this is another form of the identity. The same thing, the trigonometry identity. In fact, if we look at another case, we get the same thing. 2 Fourier and get 1. And this sine A plus B can be written as sine A plus B cosine A minus B. Yeah. This is identity. So if you present this, you say this is wrong. That means you deny the trigonometry identity. Every signal has two phase, 2 view. And which one is right, which one is wrong? This has been answered by Patrick Flandre. Yeah, 1 or 2 frequency. The empirical mode decomposition answers. So when you play 2 signals, it actually automatically gives you a beat. Is beat 1 frequency or beats 2 frequency? You cannot say that because of the amplitude change, therefore it's 2 frequency. I can actually make 1 sound, and I change my amplitude. Then, from Fourier say you have 2 frequency, but I can say, well, no, I did not. I just changed my amplitude. So there is a different interpretation of this particular signal. So because of that, Patrick, did I discuss this? We did not discuss this, right? The Patrick Flandre come up with a paper in IEEE. And that's the reason why people start to pay attention, because Patrick Flandre is a very well-known guy in signal analysis. And he, in IEEE, signal, transaction of signal processing, he said this: closed tones are no longer perceived as such by human ear, but rather are considered as a whole. If you have 2 tones, can your ear actually say this 2 tones? Depends on how close you are. If it's close enough, it becomes 1 tone, and your ear actually hear 1 tone rather than 2 tones. Now, this is get up. This is much physics, not mathematics. Mathematics means 2 possibilities. Physics means only 1 possibility. But I have to warn you here is that there are some people that train their ear to pick up 2 Fourier components. Yeah, when they hear the frequency start to modulate, they immediately say, aha, this is actually 2 tones. Yeah. There are people that can actually pick up the 2 tones. Yeah. But most people perceive only 1. For those 2-tone people, if you generate a signal with amplitude fluctuation, they will say, oh, you generated 2 tones. Yeah. So this is totally interpretation. When they say 2 tone, they are right, because Fourier has 2 tone. When they say 1 tone, right, because trigonometry tells us is one is possible. The one possibility, however, is really matched physics better than math. Yeah. So what what Patrick Flandrin did is to actually generate two-tone. And the two-tone that he generated is A cosine F1 plus A2 cosine F2. Instead of keep changing A1, A2, he reduced the first one to cosine theta. The second A is amplitude ratio. Divide this amplitude over there, A2 or A1. Frequency also defined as F2 over F1. So I have a standard frequency plus a modulator. Yeah. We want to see whether you can or cannot separate the two. So the separation is defined as if you use IMF. The first IMF components you define as D. This D minus cosine 2 theta, your standard. If the 2 equals to 0, that means, if it equals to 0, it means that you can extract the high frequency. It's complete. If it's 1, yeah, that means this 2, this is almost nothing that you can extract out. Then this becomes 1. Yeah, if it's 1, then you cannot get it out. So throughout millions of computation, he found out this. So if frequencies ratio equals to 1, near 1, you will perceive, you cannot separate in two frequencies. So that what you perceive as only 1. And otherwise, you can actually take it out as two components. So the ratio of frequency, if it's equal to 1 or near 1, your ear cannot, most likely your ear cannot do it. Now this is strictly from EMD, not from ear. And I tried there actually in the 1930s. This is a long-standing problem. They try to make people tell whether you can or cannot separate the two. Yeah, and the difference between the ear and this, there are some differences. But that experiment was very old. The difference, the results are very similar. I tried to redo this experiment here. Actually, we have somebody in the cognitive science in the psychology department. Yeah, I tried to do this, but this professor, young professor, is very energetic, but he failed to see the implication. She always get 1 or 2 persons to do this. I want to do a massive test to define the boundary to see whether this agree or disagree with the EMD. So a signal is 1 or 2 sine wave. It's not the problem. The problem is the 1 or 2 sine wave has mathematical identity. You can see it as 2 or as 1, either way. But your ear can see some as 1, some as the other one as 2. This is what what the analysis that did by Patrick Flandrin. Now, if we have a different a nonlinear pendulum, we have talked about this many nonlinear pendulum many times, and pendulum form is sharp crest, sharp trough, and we can actually take this pendulum and expand it cosine and cosine. So one of this wave automatically gets written as Fourier many components. So if you do Fourier spectrum, it's come out like this. Is this a standard? I don't think so. So if you have this, then you have the wave, the harmonics. And if you more, you can have the fifth, and so on and so forth. But this Hilbert only gives you continuous. So what happened is that the Fourier spectrum gives you lines. Instantaneous frequency gives you a continuous distribution. Which one is right? Which one is right? If you use linear superposition, you think this is right. But if you look at the problem itself, actually it's this. The frequency is indeed changing. So the fundamental mistake that Leon Cohen made is to compare apple and orange. One is average the frequency based on Fourier. The other one is instantaneous frequency based on time derivative. They are different, total different things. Yeah. So I missed this line. It means I'm wrong. There are different representations. We said many times again, these are the two different representations. Mathematically, they're both right. But physically, one is better than the other. Because if you do this, in order to if you do the Fourier, in order to reconstruct the signal, you have to include all the harmonics. If you miss one, you will never get back to the original. But if you do this, that's it. Yeah, one signal represents everything. And it will give you better resolution too. So this is the Duffing wave, and not only that, the Duffing wave can give you very minute change of frequency. This frequency is higher than this wave, so you can immediately see. So this kind of resolution is the power of instantaneous frequency. You will never be able to get it by considering mean. Yeah. Now, this is already not Fourier. This is wavelet. It gives you some local indication, but the local indication is not sharp enough. If you use Fourier, just clear, no bumps. Yeah. So this is different. So the marginal spectrum, you can see the marginal spectrum cover over a wide range. This marginal spectrum is actually for Rossler. Yeah, this Rossler have high frequency, low frequency. It actually, the phase functions start to go like this. It's already chaotic. Yeah, and if you decompose, you get two components, and the two components plus very, very small transitional error. So you have low frequency, high frequency, low frequency, high frequency. And this, again, agree. This is a low frequency, this is a high frequency. You can see the width. Yeah, but when you do Fourier, what happened? You get fundamental harmonics, all the harmonics. But this low and high, low and high, low and high, low and high were totally missed. This is physics. Yeah. So the instantaneous frequency not only give you mathematically correct, but also give you physics correct, physically correct. Yeah. This is the wavelet, and this is the Fourier. Yeah. The Rossler signal is the most rich harmonics that you can find. Why you get so many harmonics? It's very simple. When you have a Fourier, you want to use a sine wave to represent everything. But if my signal looks a sine wave, almost a sine wave, but then switch to a narrow one, and then switch to the wide one, narrow one. When sine wave come up with this, sine wave is totally incapable of doing things. Why? Because in order to fit this, I need a low frequency. In order to fit that, I had high frequency. But I have to add components after components after components to suppress the high frequency here and low frequency there. And that's why you get so many harmonics. Yeah. So Rosler has lots of harmonics, all the harmonics. And these harmonics, those harmonics, if you do an instantaneous frequency, I don't have anything over there. You don't need there. All you have is a lower oscillating frequency and higher oscillating frequency. That's all you need, indeed. Yeah. So you see what you got here is the Fourier harmonics, harmonics, harmonics. What is this Fourier? This Fourier is the weighted mean of all that. Yeah. They're low frequency, they're high frequency. So once we realize this, we would not miss that peak, because that peak is only the average peak in order to add up to the to the instantaneous to the frequency varying waveform. Now we have explained thoroughly the instantaneous frequency does not go along with Fourier's line spectrum. Yeah. Next, we come to negative frequency. The negative frequency is, again, a misunderstanding of instantaneous frequency. I'm sorry to show you all this math. All this, the first time I teach this course, I cover all these little details. And I find that when I talk about this, half of the class fall asleep. So I decide not to teach it. If you enjoy this, it's in our website, right? It's on our website. If you can go to the class notes of the first time I taught it, it's all in there. What it all takes is that the real number has a Fourier transformation from minus infinity to infinity. Then I can write as 0 to infinity and minus infinity to 0. Then, because of the spectrum is symmetric, so make a variable change, then I can actually say that my x number can be written as a real part of 0 to infinity rather than minus infinity to infinity. Okay, so this is all this mass showed up this little bit. This x equals the real part of that. Okay, having said that, my next question is, if x is equal to the real part of that, now what is the function? Take away the real. What's the imaginary part? This is the question. What's the imaginary part? It turns out the imaginary part is Hilbert transform. Yeah, this is the Gabor transformation. Yeah, if you take this integral, not just limited to the real part, positive frequency positive, and look at the imaginary part is the Hilbert transformation. All right, so this is the Gabor representation. And Leon Cohen picked this up. He said, aha, you say this H, Hilbert transformation, is from 0 to infinity. All the real number, all the positive. Then how come you can get the negative frequency out of it? That's his question. We can forget about the others. Negative frequency. This is real, this is real, this is real. And from this we can get negative frequency. Why we get negative frequency? Negative frequency is not because it's whether it's analytic or not analytic. It's because it's whether it's symmetric or not symmetric. Yeah. What happens is that any time you have a loop, outside the 0, you will have negative frequency. Yeah. When you compute the phase cover this part, and then phase cover this part. See, increase, decrease. When increase means positive, decrease means negative. So any loop means negative frequency. Any loop not including zero in it. If you include zero in it, it will never be negative, because the phase still increase monotonically. But in this, phase is not increase monotonically. This is one example. Negative frequency only for the red. Okay. Now let's see some. So the frequency value in Fourier and Hilbert analysis is a totally different meaning. One is the mean, the other is the instantaneous value. Instantaneous could be negative, but the mean still is positive. Why? Because once you go through one cycle, then it's still increasing. Let's see, if we do it by shifting, we can get this. Here is a sine wave, sine omega plus sine 4 omega. So you get this. So when you look at this, you immediately see that if I do Hilbert transformation on this green, I will have negative frequency. How do I know? Because I have multiple extrema. When I do full Hilbert transformation, the real part will increase, decrease, and then increase. That means the real part will decrease, increase. And then the imaginary part, by decrease and increase, give you one loop. Yeah. Indeed, if you look at this loop, 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 each of this loop will give you a negative value. Where's the negative value? Negative value here, 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 here. Yeah. So anytime you have multi-extrema between zero crossing, you will have negative frequency. Negative frequency is not from analytic function. It's from the fact that you have multi-extrema. Yeah. Multi-extrema means in the Fourier, in the Hilbert transformation, means a loop. Yeah. The real part, increase, decrease. That's a multi-extrema. Yeah. Increase, decrease, increase, decrease. They're all from the little loops. So in this case, I have a lot of negative frequency. And this frequency, because of that, this frequency doesn't mean a thing. How to do that? The correct way, you can even make this in such a way. You can change this 0.4 to 1. Then you look at this negative frequency. Negative frequency becomes very large. Yeah? Why is that? Because the loop getting bigger and bigger, and when this amplitude is the same, there's one point, singular point, amplitude equal to 0. So this loop is very big, this loop is very big. If the loop does not come to origin, no problem. If it comes from origin, you will have singularity points. Yeah. So how can we handle this? It's very easy. If you have multi-extrema, that means it has multiple scale. Yeah. Multiple scale should be handled with the EMD. So Hilbert transformation has a loop, means you have negative frequency. It's not because of analyticity. It's nothing to do with analyticity. Yeah. So if we do this right, we decompose. Once we decompose, this is a 0.4, this is 1, and decompose is very clean. So negative frequency problem is resolved. Yeah. So negative frequency is mostly due to riding waves. Once a wave riding on top of other, you have multi-extrema. When you have multi-extrema, you can have a problem. So MF, however, is a necessary but not sufficient. Sometimes it's already MF. Sometimes you look, there's no extrema. You think there will be no negative frequency, you may still have it. It all depends upon how the amplitude change. And that is governed by dressing and the Nato theory. We have already said that, right? So physically abrupt frequency change can give you a problem. Yeah. Because the Hilbert transformation has a certain stiffness. It cannot instantaneously loop around. So they may forgive some of the double humps. That's because 1/T there. It's not that precise. Yeah. So paradox number 5. The local influence, non-local influence indeed exists. Because this window 1/T, you have to know 1/T is a pretty sharp window. Yeah. At t equal to 0, it's infinite. All the others are finite. So this is very sharp. But even it's very sharp, we still have problems. So we can solve the problem by normalize, but the best method is by quadrature. Forget about it. Yeah. Forget about Hilbert transformation. Hilbert transformation is not the best method anyway. It will not give you the correct frequency when the signal is nonlinear. Yeah. So now you see that all their paradoxes printed in the famous book are actually very easily resolved once you understand how the frequency is defined. Yeah. And then once you know how frequency is defined, you can discuss instantaneous frequency problem with anybody in the world. When they have this sort of unreasonable challenge, you can immediately point out what's the correct answer to them. Yeah. So abrupt change, we do have this Wavelet Resolution. We do have we do have negative frequency here. Not only that, this frequency is not constant. It's pretty good, pretty bad. So when we discuss instantaneous frequency, we have already discussed how to handle this. How to handle that? Normalize the amplitude. Once you normalize the amplitude, we will get a constant frequency. Yeah. So, so all of this problem that they raise has a reasonable method to resolve it. Yeah. So the non-local thing, we use normalize and we use quadrature. So in summary, yeah, the so-called paradox are really not a problem. Yeah. Once the misconception are clarified, to begin with, the instantaneous frequency has a total different meaning against the mean. In other words, if somebody come over here saying that you define, how do you define velocity? He says velocity is the average from point A to B. Then he found that at some time you are traveling, even though you arrived at the same mean velocity, but sometimes you can travel faster and slower. And that doesn't mean that it's wrong. It's because you are more precise. See, you can have from A to B, your velocity can be like this, and you say this is an average. And his challenge is almost saying that your instantaneous frequency is not the mean. Of course it's not the mean. Yeah, because this is average. This is instantaneous value. Yeah, that the instantaneous value deviate from the mean. It's normal. It's not abnormal. Yeah, so instantaneous frequency for special monocomponent function only. Yeah, But this mono component is not sufficient. It's only necessary. Yeah, we saw that. So even with IMF, we still have to pay attention to Bedressen, and the better solution is quadrature. So now we know that the instantaneous frequency has a clear difference in physical meaning and mathematical meaning than the so-called frequency by Leon Cohen. Leon Cohen's frequency is defined as mean. My instantaneous value deviate with mean is totally legal and totally reasonable if my phenomenon is non-stationary. I should not have all the way constant. Who said my frequency has always be that? So all his misconcept mostly is because of this. The other one is because of the misunderstanding of Hilbert transformation. Hilbert transformation, you cannot take any function and do Hilbert transformation and get instantaneous frequency. Hilbert transformation need to be operated on monocomponent. Even that will not guarantee you're right because of these theorems. Right? So the best way is go through EMD and quadrature. Then you will find out the instantaneous value without any problem. Yeah. Now, let me add one more. He did not even ask. I can tell you there's one additional thing that he didn't catch. That is, if I compute the instantaneous frequency actually, the mean may be slightly different from what he called the mean because there are harmonics in there. Yeah, if they compute their mean, they have to consider harmonics. So the instantaneous frequency for nonlinear, it fluctuates. Yeah, so for nonlinear, in his book, he did not even mention nonlinear because he knows that the regular wire cannot do nonlinear. Yeah. So we know now our method and the method that you people learn now is way beyond what other people has already thought of as time frequency analysis. You have the real means of time frequency analysis now. Okay? All right. This is the end of my lecture. Any questions? Takui, is this a lecture okay compared to face-to-face?
Me.
Hello.
Okay.
Yeah. This is the gentleman that took me around, showed me around. Tokyo, the train system is so complicated. Without him, I would be totally lost. Yeah. Thank you again.
You're welcome.
Yeah. You have any questions? No? We are going to have this course class will still meet here, but will not make a connection to Tokyo anymore, right? So the core is already complete, and all the others are applications. So for the student here, you will have extra month of application. Yeah, well, that will be taught by other faculty members. All right. If you don't have any question, then thank you very much. Thank you for taking the course. I hope you learned something. Sayonara.
Thank you very much.
Thank you. Yeah.
Bye.
By the way, if you have any question, you can send us email either to me or to our assistant, Ms. Liu. Ms. Liu, yeah, here. You can send a question to her to clarify when you do your homework, okay?
Okay.
Bye-bye.
Bye-bye.
Bye-bye. All right. So 你们听了这个，现在我们把这个基本的理论都讲完了啊。以后下一个月12月，我们主要是讲一些应用啊，那么让你们对这个方法有更清楚的了解，就是它我们怎么用，讲了这么大理论，什么地方可以用。OK， 好，你们还有什么问题没有？有什么要讨论的？我这堂课以后我不来上课了，有没有问题？没有问题，我们下课喽。OK， 拜拜，下课。